Welcome all. With the discussion of RSA encryption, the topics of unit number 4 discussion is complete. But then I thought maybe if we can solve one or two problems on some topics in this unit, we can have more exposure of different kinds of problems. So we'll just look into the idea is to look into some problems in this unit. Consider another question on RSA encryption, which is as follows. Given the public key, given the public key E comma N equal to 7 comma 55, encrypt plain text, PLAN. Okay, this is the message to be sent. We need to encrypt that. Where the alphabets A, B, C, so on until X, Y, Z are assigned the numbers, are assigned the numbers 2, 3, so on 26 and 27. Give the cipher text, find the private key D. Okay, so this is the question solution. Now in this question, if we see, they have already given the choice for E and N. Okay, so E they have given to be equal to 7 and N is given to be 55, and this N we need to write it as product of two primes, which is straightforward here, 5 into 11. Anyway, this is the example just to learn the this RSA procedure, but then in actual scenarios these primes will be really big. Only then the encryption will be secure. So this, let us call them as P into Q. Then for this N, we have the torsion phi of N. Since both numbers will be prime, here we'll have P minus 1 into Q minus 1, which is equal to 5 minus 1, 4, into 11 minus 1, 10, which is equal to 40. Okay, so this is our totient. Then observe that this E is already chosen to be 7, and definitely E and that is 7 and this phi of N 40 are co-prime, right? Relatively prime. Also GCD of E comma phi of N, which is nothing but GCD of 7 comma 40, it is equal to 1. So they are co-prime. That is also done. So next we'll proceed for the computation of D. What is D? D is the key used for decryption, which will be a private one. So to compute D, we have the relation ED should be congruent to 1 mod pi. That is 7D should be congruent to 1 mod mod 5, 5 that is 40. Okay, so this would imply 40 should divide by definition 7d minus 1, which again by definition of this 40 divides a number divides some other number. That would mean 7d minus 1 is a number which can be written as 40 into some number. Let me call it as say k. Okay, now in other words we have an equation which looks like this: 7d plus 40k, sorry, minus, right, 7d minus 40k equal to 1. Okay, one thing is we can keep on trying different values for d as we did in the previous question that we did yesterday, and say d equal to 1, we end up with 7 into 1 minus 1, which is 6. 40 does not divide 6. So you can go for say maybe somewhere near to 70. 7 6 times is 42. 42 minus 1 doesn't work for 6. So you can keep trying like that and you will get. But there is another way to do it, which we have learned already in finding GCD, right? Here what we can do is, see, basically we need, suppose we find a GCD of 7 and 40, which we know it is 1, but through that procedure of finding GCD, we'll get steps which we can build back to find a uh, linear combination of this form: 7 into something plus or minus 40 into something equal to 1. So that's what we are aiming at now. Okay, so we should know either ways. This might take more time what we are doing now, but better to know both the ways. Trial and error everybody knows, so nothing special there. So you can get by trial and error. One option is to go for trial and error. Now what we are doing here is option 2. Option 2, GCD method. I'll just call it. There is nothing like GCD method, just to understand. Okay, GCD method where we find the linear combination. So we'll go with option number 2. So what is it that we want to do? We want to find HCF or GCD for 7 and 40. So 40 equal to 7 into something plus a remainder. So very simple numbers, no? We can do it very easily. So what should we write here? 7 into 5 plus 5, 35 plus 5. Then this 7 comes here and 5 will be taking place of this as we have discussed before. So 7 equal to 5 will come here. 5 into something plus a remainder. So 5 into 1 plus 2. And this 5 will come here, and this 2 into 2 is 4 plus 1. Then what do we have? 2 equal to, using 1 we should express 1 into 2. So there it ends. So definitely, as we know already, 1 is the HCF. But then our goal is to find the linear combination so that we can find this D. Okay. So 1 is there. This 1 we need to write it as linear combination of 7 and 40. Let us start to do it. 1 equal to by this particular step, 5 minus 2 times 2. 2 times 2. And by this step, this 2 can be written as 7 minus 5 into 1. 5 minus 2 times 7 minus 5 into 1. Okay, let us simplify that. This can be written as minus of minus plus 2 times 5 plus 1 times 5. So totally 3 times 5 minus 2 times 7. Okay, by this particular step 5 can be written as 3 into 5 can be written as 40 minus 7 into 5. 40 minus 7 into 5. 7 into 5. What else do we have? 3 into 5 is replaced by 40 minus 7 into 5 minus 2 times 7. This is what we have. So that will be equal to 3 times 40. Okay, one job is done. Then 3 times 40 minus 21 times 5. Oh, wait. 4, which are the numbers? 7 and 40, right? Okay. So 7 is our focus. 3 times 5, 15 times 7 and 2 times 7. So minus 17 times 7. Okay. This if we compare it with what was the expression? We have 7. I'll just write it in a different color. We have already got it here. I'll just write it here so that we can compare. So what do we have? 7d minus 40k equal to 1 is what we have. 1. So if you compare, in place of d we have minus 17, and in place of what is this, k will be minus 40. I mean 40 into minus k, we can think like that. So k will be equal, minus k equal to 3 or k equal to minus 3. Anyway, k we are not bothered here. What we want is this d. Okay, so this implies d equal to minus 17. But remember, during encryption generally we go for positive value. Okay, so we can convert this to positive value, very simple. So what, when we say d equal to minus 17, that means minus 17 mod 40, right? Minus 17 mod 40. Now things are happening with mod 40. 17 minus 17 mod 40. We want a positive number. Okay, minus 17, we want a positive number which is congruent to minus 17. So I'll write like this: minus 17, we want x, a positive x, such that minus 17 should be congruent to that x mod 40. That is, we'll just make a separation here. Okay, it is, by definition, what do we have here? 40 should divide minus 17 minus x. Okay, now as you can see, this d need not be unique, of course, but let us take the simplest possible value. So what value of x will make it divisible? Minus 17 minus something should be, if I take, if it is just equal to 40, that is also enough, right? So how can I make this total as 40? So 40 and 17, difference is how much? We have 17, 27, 37 and 40. So 23 is the difference we have. So if I put that 23, it is complete. What is happening? Not equal to divides, right? 40 divides this number, that is, should be equal to 40 into something. This total is minus 40, which is nothing but 40 into minus 1. This implies 40 divides minus 40, of course, minus 17 minus 23. So this would imply x equal to 23. Okay, x equal to 23. As you can think, you can also choose other numbers, so such that this will be 40 times minus 2 or 40 times 3 or whatever you can choose accordingly. 40 times, I think negative only you might get, right? The bigger number you take, you might get negative, but that is fine, no problem. This number we want it to be positive, we have got it. So what do we have then? X is 23. Okay, so that is minus 17 is congruent to 23 mod 40. So don't worry about this x, d variable names and all. Basically we wanted one number congruent to minus 17 under mod 40. We have got it. So d, instead of that negative value minus 17, we take d equal to 23. Okay, d equal to 23. So what do we have now? Uh, we got our private key. That's what they had asked, right? What was the question? Give the cipher test, find the private key D. Therefore, n comma D equal to n is 55. 55 comma 23 is the private key. Okay, let us highlight that answer. Now the next thing is to give the cipher text using this for plan. Okay, so plan, the text plan would be represented by the integers as message number 1. That is, for each text, I mean each character in the text, we call it as message individually. Say m1, m2 and so on, that is what is our p. Okay, so according to this, where does our p come? P is a 16th letter, no? So first letter is given the number 2, second letter is given the number 3. So 16th letter will be having the number 17. P, L. L will be L. L will be 12. 12th letter. So starting with 2, you will get 13. And A. A is first letter and its integer correspondingly is 2. And N. 14th letter, no? So this will be 15. So this is the set of integers we are looking at, which we want to encrypt now. So for p equal to 17, okay, cipher 1, that is encrypted letter for p will be c1 equal to, what is the formula? m1 m1 m power. Basically we are talking about first letter, so I am writing m 1 power e m1 power e mod n, that is equal to m1, which is 17, power e, that is 7, 17 power 7 mod n, that is n is 55. Okay, so we can find it using calculator as we did in the previous class. You can just go for 17 power 7, 17 power 7, which will give us, I'll just do it as a rough work, 17 power 7 will be 410338673. Okay, this, when you divide by 55, what is the remainder? That is that is what we want here. So let's do the division. 55, I mean 17 power 7 divided by 55, that is giving us 7460703. There is a gap here, it just came like that, no gap. 703.14 something is there. Okay, so the point is, if I leave that point, if I just take this, when I do the division, we'll get some remainder less than 55. That is the idea. So let us do that. 55 into 746 0703. So that is giving us 410338665. So the remainder turns out to be how much? 8. Right? 8. So we have, this is equal to 8. Okay, so this will be 8 means, actually what will be the text? So C1 equal to 8, which is equal to A, B, C, D, E, F, G. G is the seventh. G is the seventh letter, so it will have the number 8, right? Since it is starting from 2, G. Okay. Similarly, when you calculate for F equal to F, which is equal to EFG. So, wait. What is the next letter? We have L. Okay. What is the number for L? We have 13. And when we perform all this, we end up with the value which is 7. Okay. So that will be the letter F. Because sixth letter is F and it will have the number 7. Similarly, we have next letter A, which is equal to 2. When we perform this step, we end up with the number 18. And 18 means we should take the 17th alphabet. Q. So Q is the 17th alphabet, it will have the number 18. So we have Q. Similarly, for finally N has the character, I mean, has the integer value 15 associated to it. And in this case, you will end up with the answer 5. Okay, do work that out. In the very similar way that we did for P. 5 means fourth letter is A, B, C, D. So this will be D. Therefore, the cipher text is GFQD. So the message that is being sent is plan, but the ciphered, that is encrypted message, is GFQD. Okay. In case we want to do decryption, we have that expression, no, which I think we did look into encryption, decryption also yesterday. For each letter, instead of this equation, you will be taking the other equation. So from M we got C, no, from C we should get back M. So M, I'll just put it in bracket, they have not asked here. M will be equal to C power D. So here the power is the encryption one, here the power is the decryption one. C power D mod N. So for each one you will be taking, for M1 you take cipher 1, that is you take 8. For M2 you take C2, that is 7, and so on. Okay. That if they ask, you should know, no? That's why I'm just mentioning. So that's how you'll have questions on RSA public key. Okay. Another question I'll just give. You can try it in very similar way. Just write it here. So the question wordings are same. Okay. The difference being that whatever the difference is, that I'll just mention here. E comma N is given to be 3 comma 65. That is one change. And the plain text is hi, HI. Okay. Of course, maybe nobody would encrypt message hi. Doesn't look any. Anyway, our goal is just to learn it. So, just an example. Alphabets are assigned 2 to 27. Everything is same. I'll just put dot dot wherever the question is same. So, give the cipher text and find D. Okay, everything is same. I'll just underline by green color here. This is changed. This is changed. Everything else will be same, the question. Okay, so the green. So do solve it and let me know the answers. Now one more idea is, okay, RSA public key, if you are clear with that, it should be fine. Another idea is this Euler's theorem. There some variety of questions can be asked. So let us look into maybe one or two questions. What does Euler theorem tell? We have seen it now. Euler's theorem tells that Euler's theorem, it states that if you have two numbers, say a comma n, m whose GCD is 1, then a power phi of m, that is the quotient of m, will be congruent to 1 mod m. Okay, so this actually we saw that it appears in RSA public key encryption, but here we'll just look at some problems based on this particular theorem. For example, find the last two digits of 3333 power 4444. Okay, such a huge number, no? We might not even bother to calculate it. Using this technique, we can escape all the calculations and just find what will be the last two digits. Now, if you're talking about last two digits, one easy way to do that is whatever the number is, we just divide it by 100, right? When we divide by 100, whatever the remainder that we get, those two will be the last two digits, right? For example, if I take, say, if I divide, say, 8325, so here I'll get 83. How much? Yeah, 83 times if I take, I'll get 83,025 will be the remainder, and so on. Last two digits will come out. So, since you are talking about remainder, what we are looking here is to go into mod 100. Okay. Now, let us first make a note that solution finding the last two digits, the last two digits of this particular number the last two digits. Okay, sentence finding the last two digits of can be. Okay, you can just ignore this finding. The last two digits of this can be obtained by reducing this number mod 100, as we saw here. Okay, now to do that, we need to first start by looking into numbers which are co-prime. Now here, if you look at these two numbers, 100 and 3333, for 100 we have 100 can be written as 25 into 4, which is 2 square into 5 square. 2 is definitely not a factor of, let us look at this particular number. 2 is definitely not a factor of double three. 5 is also definitely not a factor of double three, right? It should end with 5 or 0 in that case. So definitely we know that GCD of these two numbers, double three and 100, is definitely equal to 1. That means we have this particular property that is happening. Okay, that means we can first go for phi of m. Let us calculate that. Okay, so phi of 100 is equal to phi of 2 square into 5 square. So phi for a composite number is given by n into prime 1, which is 2. So 1 minus 1 by p1, 1 by p1. We solved a question yesterday, no? Yesterday, maybe 2 classes before. 1 minus 1 by p2. Second prime number is 5 here in the prime factorization. And this turns out to be how much? 100 by 2 is 50, and here we'll have 4 by 5. Okay, so this will give us 40. That's a very interesting thing, because we can now look at this property a power phi of m, that is by Euler's theorem, a power 40, that is double three power 40, will be congruent to mod 1, will be congruent to 1 mod 100. Okay. Now what we want is, from this particular power, that is double three power 40, somehow we must make nice manipulations so that we end up with double three power double four. Okay, so slowly we'll have to take it to that. First of all, let us see how much we should raise this to go somewhere near that. So for that we can go for division algorithm. Apply division algorithm on double four and 40. We want to establish a connection. So we get double four equal to 40 into, okay, 444 we get, and a 0. So 111 into 4 will give us 444, 10. So 4440, 4 is remaining plus 4. This would imply, what is it that we want now? Okay, not implies. Let us start with 40. 40, how to take there? Okay, let me name this as a equation 1. Equation 1 would imply that double three power 40, okay, power 40 whole power 11. Now my target is this: whole power 11 will be congruent to what is right side here, 1. 1 power 111 mod 100. Okay, still that is not enough. We need this extra 4, so we'll have to multiply that. This would imply double three power 40 whole power 111 into 3 power 4. Oh, sorry, not 3. Double three whole power 4. So why we are doing this? So that now the total power is double four as we planned. I mean, as it is required. So here what we should do, 1 power 111 into, so we should multiply it on both the sides. Double three power 4 mod 100. So we have just multiplied this required number on both sides here. Okay. So totally this would imply, as we planned, the total power in LHS will be 4444. That will be congruent to 33, not 33, double three power 4. Now this double three we have 4 times. Okay. Now each number, when we take mod 100, what do we get? Double three mod 100 is equal to 33, right? So for each time when we take mod 10, we'll get 33 for third number 33, and fourth number also 33. So we actually get 33 into 33 into 33 into 33 mod 100. Okay, why is this happening? Maybe I'll write it in bracket, because 3333 is congruent to 33 mod 100. Okay, I missed out a 0 here. Let me add it, 100. Okay, so that would imply if you just raise it to power 4, this will also get raised to power 4. That's what is happening here. Okay, maybe we could have written directly there 33 power 4. So we have 333 power this number is congruent to 33 power 4 mod 100. Okay, observe where is this huge number and where this such a small number, no, compared to this. That is the power of this Euler's theorem. Okay, this implies uh, this implies is congruent to 33 power 4. That's very easy to find using calculator, of course. 33 power 4 is 1185921. Okay, mod 100. Okay, and we know that, but this 1185921 is congruent to 21 mod 100. Very simple. When we divide by 100, 21 will be the remainder, last two digits. There, see, this is A is congruent to B congruent to C, mod same 100. Therefore, we can conclude that therefore 3333 power 4444 is congruent to 21 mod 100, which implies 21. Okay, the last two digits, the last two digits of this big number is 21. Okay, that's how we approach this problem. Consider another question. Let me highlight this. Okay, find the last digit of only the last digit of 55 power 5. Okay, solution. Now observe that in previous question, how did we start with? We had, yeah, so since we are talking about last two digits, we were looking at GCD of that base 3333 and 100. And here GCD of, no need to write GCD, the GCD of, we are talking about last digit, so the number of interest is 10 and the base here is 55. This is not equal to 1, right? This is equal to 5. So we cannot just go straight away like we did in the previous question. Okay. So this implies 10 and 5, 10 and 5 are not co-prime or relatively prime. So what to do? We definitely know that this 55 has the prime decomposition of 5 into 11. Okay. Now this 11 is co-prime with 10. Okay. So we'll have to make use of that information and somehow approach to 55. Okay. By using some manipulation. Let us see. But GCD of 10 and 11 is 1. Thus, by Euler's theorem, what does the theorem tell? A power phi of m is congruent to 1 mod m. Okay. So what was the base in the previous question we took? Is, yeah, of course, double three double three. So here we want the base to be 55. We start with 11. Okay, 11 power, because a and m we can choose however we want. But this is the base we want. We start with 11. So 11 power 5 of 10, the quotient of 10, mod sorry, congruent to 1 mod 10. Okay, this uh, we know that 5 of 10, 5 of 10 will be how much? 5 of 10, how do we find that? For 10 we have the prime factorization 2 power 1 into 5 power 1, which is, then we get n into, that is 10 into 1 minus 1 by p1, that is 2, into 1 minus 1 by p2, which is 1 by 5. Okay, this will turn out to be how much? 10 into 5 into 1 by 5. Okay, so this number turns out to be 4. This then this step would imply 11 power 4 is congruent to 1 mod 10. Okay, now our target is to get 55 power 5. So 55 power 5 means 55 power 5 can be written as 11 power 5 into 5 power 5. That means first of all I want 5 in the power. So this would imply 11 power 5. Okay, let me write it separately. You can write directly once you understand. 11 power 4 into 11 power 1 is equal to 1 into 11 power 1. Multiplying it on both sides congruent to mod 10. Okay, then we have 11 power 5 congruent to 11 mod 10. You can skip some steps here, but I'll write all each and every small step. Now we want 5 power 5. So 5 power 5 into 11 power 5 should be congruent to 5 power 5 into 11 mod 10. That is, this would imply 55 power 5 is congruent to 5 power 5 into 11. How much is 5 power 5? 5 power 5 into 11. How much do we get? 5 power 5 into 11. So that will be 34375. 34375. Okay, mod 10. But let us, okay, mod 10. Let us write how we wrote in the previous. Actually, we can write here itself. This is congruent to, straight away we know that last digit is 5, right? But 34375 is congruent to, when we divide this number by 10, the remainder will definitely be the last digit 5 mod 10. So A congruent to B congruent to C. Therefore 55 power 5 is congruent to 5 mod 10. That is the last digit, the last digit of 55 power 5 is 5. Okay, that is the conclusion we make. Okay, then yeah, so that should be it. Uh, just wanted to show you some problems that can be asked on Euler's theorem, and also look into at least one more question on RSA encryption, which we have successfully done in this session. So any doubts, you can approach me and ask and get it clarified. Okay. So thank you all. See you in the next class.